For decades, the idea of quantum computing has felt like a mirage on the horizon, a shimmering promise of unimaginable computational power, always just out of reach. It was the stuff of theoretical physics labs, a futuristic concept that seemed destined to stay in the future. But that's changing. We are living in the dawn of mainstream quantum computing, an era where this technology is finally stepping out of the lab and into the real world. The United Nations has even declared 2025 the International Year of Quantum Science and Technology. This isn't just a symbolic pat on the back. It's a global recognition that we've hit a critical turning point. The conversation is no longer about if quantum computers will be useful, but when and how. So today, we're going to dive into how this revolution is happening, what's making it possible, and which industries are already being transformed. To understand the quantum revolution, we first need to understand why it's so different from the computers we use every day. Your smartphone, your laptop, even the most powerful supercomputers all work with bits. A bit is a simple switch. It's either a 0 or a 1, on or off. All the magic of modern computing is built on trillions of these simple binary decisions. Quantum computers, however, play by a different rulebook, the strange and wonderful rules of quantum mechanics. Instead of bits, they use qubits. A qubit can be a 0, and it can be a 1. But here's the twist. Thanks to a property called superposition, it can also be a combination of both 0 and 1 at the exact same time. Think of it like a spinning coin. While it's in the air, spinning, it's neither heads nor tails. It's in a state of both possibilities at once. Only when it lands, or when we measure it, does it choose a side. A qubit is like that spinning coin. This ability to exist in multiple states at once means quantum computers can perform a mind-boggling number of calculations simultaneously. To give you a sense of the scale, a quantum computer with just 300 stable qubits could, in theory, perform more calculations in a single instant than there are atoms in the known universe. But superposition is only half the story. The other key ingredient is entanglement, a phenomenon Einstein famously called spooky action at a distance. When two qubits are entangled, their fates are linked. No matter how far apart they are, one in New York, the other in Tokyo, the state of one instantly influences the state of the other. Measuring one to be a 0 will instantly force the other to be a 1, or vice versa. This interconnectedness allows for a level of parallel processing that is simply impossible for classical machines. It's this combination of superposition and entanglement that gives quantum computers their power. They are uniquely suited for problems with a massive number of variables and potential outcomes. Problems like simulating the behavior of complex molecules or optimizing a global supply chain. For most of its life, quantum computing has been held back by one huge problem: noise. Qubits are incredibly fragile. The slightest vibration, a tiny change in temperature, or a stray electromagnetic field can cause them to lose their quantum state. This is a process called decoherence. This noise introduces errors into the calculations, making the results unreliable. We've been living in what's known as the noisy intermediate scale quantum era, or NISQ era, a time of powerful but error-prone machines. But the years 2024 and 2025 have marked a turning point, with a series of massive breakthroughs in quantum error correction and qubit stability. We are finally learning how to build a quiet room for these fragile qubits to work in. The biggest trend is the shift from just counting the number of physical qubits to creating what are called logical qubits. A logical qubit is an abstract, more stable qubit created by encoding its information across multiple physical qubits. Think of it like carrying a very fragile, priceless vase. Instead of having one person carry it, you have a team of people carrying it together. If one person stumbles, the others can compensate, and the vase remains safe. This redundancy allows the system to detect and correct errors in the individual physical qubits, creating one highly reliable logical qubit. In a landmark achievement, researchers from Harvard, MIT, and Quera Computing demonstrated a processor with 48 logical qubits. This wasn't just a static demonstration. They were able to run complex algorithms while the system corrected errors in real time. This was a huge step forward, earning a Physics World 2024 Breakthrough of the Year award. Meanwhile, Google Quantum AI hit another critical milestone with its new Willow processor. They proved that as they used more physical qubits to encode a logical qubit, the error rate went down exponentially. This is known as operating below the threshold, and it's considered a fundamental requirement for ever building a large-scale, fault-tolerant quantum computer. It's proof that this error correction strategy actually works in the real world. IBM has also made huge strides, but from a different angle. They demonstrated that their advanced error correction algorithms can run on commercially available, off-the-shelf AMD chips, the kind you might find in a gaming PC, at speeds 10 times faster than needed to keep pace with their quantum processor. This is crucial because it means we might not need to build expensive, custom hardware for every single part of a quantum computer, potentially making them more cost-effective to build and scale. Beyond just correcting errors, the raw stability of qubits is improving dramatically. The Paris-based startup Alice and Bob developed a special type of qubit called a cat qubit, which can resist one of the two main types of quantum errors for over an hour. That is millions of times longer than the coherence times of typical qubits, which often last for mere microseconds. These breakthroughs are not just small incremental steps. They represent a fundamental shift, moving quantum computing from a theoretical curiosity to a practical problem-solving tool. So with these quieter, more reliable quantum computers, what can we actually do? The revolution is already beginning in several industries, with financial services and pharmaceuticals leading the charge. The complex, quantum world of molecules is a perfect match for quantum computers. A classical computer struggles to accurately simulate even moderately sized molecules because the number of possible interactions between electrons grows exponentially. This has been a major bottleneck in developing new drugs and materials. Quantum computers, operating on the same quantum principles as the molecules themselves, can simulate these interactions with incredible precision. This promises to slash the time and cost of developing new medicines, a process that currently takes an average of 10 to 13 years and costs over $2.5 billion per drug. Big pharmaceutical companies like Merck, Roche, and Amgen are already filing patents and partnering with quantum firms. For example, a collaboration between the quantum company Pascal and Qubit Pharmaceuticals used a neutral atom quantum computer to model how water molecules affect the way a drug binds to a protein. This is a subtle but critical detail that is incredibly difficult for classical computers to simulate accurately. In another case, the biotech company Polaris QB is using D-Wave's quantum annealing system to search for new drug candidates. They can explore billions of potential molecules in a matter of weeks, a massive leap from the few thousand that can be analyzed with traditional methods. Beyond drug discovery, quantum computing is being applied to protein folding, which is essential for understanding diseases, and even personalized medicine, where quantum machine learning could analyze a person's genome to create custom treatment plans. This same power applies to materials science. Automakers like Toyota and Mercedes-Benz are exploring how quantum computers can help design next-generation batteries, like solid-state batteries, which could offer faster charging and higher energy density for electric vehicles. The financial industry is another prime candidate for a quantum overhaul. It's an industry built on complex models and massive data sets, making it ripe for disruption. It's estimated that quantum computing could start to have a significant impact on financial services within the next 5 years. One key area is portfolio optimization. Finding the perfect balance of risk and return across thousands of different assets is a monstrous computational task. Quantum algorithms can explore a vast landscape of possible investment strategies simultaneously, identifying more efficient portfolios. Goldman Sachs has already used quantum algorithms to speed up its risk analysis by up to 25 times compared to classical models. HSBC has used quantum simulations for derivatives pricing, cutting pricing errors by around 22%. Quantum computers also offer a quadratic speedup for Monte Carlo simulations, which are a cornerstone of financial risk analysis. This allows banks to more accurately assess risk, conduct stress tests, and meet regulatory requirements. And while quantum computers pose a threat to today's encryption standards, they also offer the solution: quantum cryptography. Major banks like JP Morgan Chase are already adopting quantum-based security methods to protect trillions of dollars in annual transactions from a future quantum attack. The race to build this quantum future is a global effort, involving a dynamic mix of tech giants, innovative startups, and government research labs. And they're not all placing the same bet. Different teams are pursuing different types of qubits, each with its own strengths and weaknesses. The tech giants are leading the charge with massive investments. Google Quantum AI and IBM Quantum are pioneers in the world of superconducting qubits, the technology behind many of the early breakthroughs. IBM even put the first quantum computers on the cloud for public use and has an ambitious roadmap aiming for a system with over 4,000 qubits by 2025. Microsoft is taking a more ambitious high-risk, high-reward path with topological qubits. In theory, these are naturally stable and resistant to noise, which could make building a large-scale computer much easier, though the technology is still in its early stages. Amazon, with its AWS platform, has taken a different approach, creating a marketplace called Amazon Bracket that offers access to quantum hardware from a variety of different providers, allowing users to experiment and find the best tool for their job. But it's not just the giants. A vibrant ecosystem of startups is exploring other paths. Companies like IonQ and Quantinuum are leaders in trapped ion qubits, which use charged atoms held in place by electromagnetic fields. These qubits are known for their high stability and long coherence times. Others, like PsiQuantum and Xanadu, are building photonic quantum computers that use single particles of light as qubits. A major advantage here is that they can operate at room temperature, potentially reducing the immense cost and complexity of the cryogenic cooling systems needed for other approaches. Then you have neutral atom qubits, used by companies like Quera. This approach, similar to trapped ions but with neutral atoms, is showing great promise for scaling up to a very large number of qubits relatively easily. This diversity is a sign of a healthy, competitive field. It's still too early to know which technology will ultimately win out, but the competition is accelerating progress for everyone. Despite this incredible progress, the road to a full-scale, fault-tolerant quantum computer is still filled with challenges. The biggest is simply scaling up. Going from a few thousand qubits to the millions needed for truly world-changing problems is a monumental engineering task. As you add more qubits, the complexity of controlling them and keeping them isolated from noise grows exponentially. Another major challenge is the workforce gap. The demand for people with skills in quantum physics, computer science, and engineering is exploding, but the supply of qualified talent is lagging far behind. Some estimates suggest there's only one qualified candidate for every 3 quantum job openings. Finally, the transformative potential of quantum computing has sparked a geopolitical race. The United States, China, and the European Union are all investing billions of dollars in national quantum initiatives, recognizing that leadership in this field will bring a significant strategic advantage. So what does the road ahead look like? In the near term, we'll see a rise in hybrid quantum classical systems, where quantum processors act as specialized co-processors, tackling specific parts of a problem while working alongside classical supercomputers. We'll also see an explosion in quantum software and algorithm development. A particularly exciting area is the synergy between AI and quantum computing, where AI can help design better quantum hardware, and quantum computers can accelerate complex machine learning tasks. The ultimate goal remains a large-scale, fault-tolerant universal quantum computer. It's hard to say when we'll get there, but the pace of innovation is faster than ever. The dawn of mainstream quantum computing is here. It's a time of immense change and opportunity. The quantum revolution is not just on the horizon anymore. It has already begun.